Good morning, guys. Welcome back to another lecture on linear algebra. We finished. What did we finish? We finished the chapter on vector space and subspaces, with the last lecture being a change of bases and the rank nullity theorem. That took a little longer than expected, but we got it done. So now we're going to open up to a new chapter, another more confusing type of chapter, but again, I will do my best to help you out or help you understand this concept and how to solve this problem. At the same time, I will provide videos from other creators to help you get a better understanding with the concept, since I think a good chunk of those videos, or I think it might just be one video, but a good chunk of those will mostly emphasize on understanding the concept and not learning how to solve the problems, because I feel like understanding the concept is a lot more important and it will actually help you solve the problems a lot quicker, and as well as give you an understanding on what are you actually doing. So we're gonna get started with linear transformations, which wasn't a fun one when I did it, but I'm here teaching it, so let's go ahead and get started. So we're gonna do a little quick introduction on linear transformation, and so in this chapter we're gonna be mainly discussing about the functions that map a vector space V into a vector space W. So this, you can kind of say this is like change of bases, where you go from one base to another. But that's not necessarily the case. It's kind of like the same concept, really. The only difference is you're going from one vector space to another. When you do change of bases, you're in the same vector space and you're not really doing much of a linear transformation. You're just kind of like shifting things. Which, I mean, I guess you could say it is a linear transformation, but they're two completely different things. You can kind of argue they're like somewhat similar. Some people can say they're kind of the same, but the actual concept are two different things, and I'll explain it to you a little bit as we move along. So it is a function. Like I said, it is a function that maps a vector space V into W, and it is denoted by T semicolon V transfer W, where V is the domain of T and W is the codomain of T, and T is the actual function. It's basically the instructions on how to go from vector space V to vector space W. And so if we have a vector V that's in capital V, and W that's in capital W, um so we have those two vectors such that the linear transformation of V is equal to W, then W is the image of V under the transformation, and the set of all images of vector in V is the range of T. Additionally, the set of all vectors V in the vector space V such that TV is equal to W is called the preimage. And so a little representation that I made here is we have the vector space V on the left side, and we have a vector V. And so what we're gonna do is that we're gonna look at this instruction manual T, and it's gonna give us like a little path, a little journey, little couple steps that you have to do to get to the vector space W, and it'll give you the vector W. And so the vector space W, a section of it will be considered the range of that function, and then the vector space V would be considered the domain of that function. And like I mentioned, V is a domain, W is the codomain. If it was the other way around, so TW is equal to V, then W will be the domain and V will be the codomain. So yeah, that's not pretty much it. So now we're gonna continue and be more specific with the linear transformations, because this function t can do a bunch of things, but we're only going to be focusing on a certain portion of them because this is linear algebra. And so the functions that preserve the operations of the vector addition and scalar multiplication are what are known as linear transformations. So we can have a function, the function t, and it can do a bunch of crazy transformations. Some of them expanding to like so many dimensions. All of them can like expand to a point or something like that. But the ones that we're going to focus on are the ones that preserve the scalar multiplication and vector addition. And so what that means is we have our little two equations that look a little familiar when it comes with vector space and subspaces. Hello, welcome back. And so we are basically, or this is basically telling us that the linear transformation of u plus v is the same as the linear transformation of u plus the linear transformation of v, and then the linear transformation of cu is the same thing as c multiplied by the linear transformation u, such that c is a constant, u and v are vectors. So you've probably seen this equation so many times, and so what we're gonna do in some of the examples is show if some of these linear transformations that we're given are actually linear transformations, and it's pretty much our starting point on the left, and we have to show that it is also equal to or any point to the right, and you have to do like a bunch of steps, which hopefully you know how to do. If not, we're gonna be doing these practice, and hopefully it will become much more clear, much more better. So the reason why a linear transformation is considered an operation preserving is because the result of the transformation is the same whether you do the operation of addition or scalar multiplication before or after the linear transformation is applied. So back to those two equations that we have up here. On the left side, we have for the first equation on the left side, we have the vector addition applied first, and then we have the linear transformation applied after. On the right side, we have the linear transformation applied first to each one, and then you add them together. And for the second equation on the left side, we have the scalar multiplication applied first, and then the linear transformation. And then on the right side, we have the scalar multiplication multiplied by the linear transformation. In other words, because multiplication is kind of like commutative, you can do the transformation of the vector first and then multiply by the scalar. And so the two simple linear transformations that you should be familiar with are the pretty much the most obvious one. So you have the trivial one, the zero transformation. So any linear transformation of a vector is equal to 0 for all vectors v. And then the identity transformation, where the transformation of the vector v is itself, and that's for all vectors v. So now we're going to discuss about properties of linear transformation. And so we're gonna start off with a givens. So we're gonna let t be a linear transformation from v to w, and where vectors u and v are in the vector space of v. Keep in mind v and w are vector spaces. Then the following properties are true. So the first one is going to be that the linear transformation of 0 is equal to 0, which intuitively makes sense because we're working with linear algebra and linear transformations. When we shift the what do you call it? I guess in this case our graph or changing from one vector space to another. The thing that makes linear algebra linear is two things. The first one is that each vector space or each dimension that you're working with, the coordinate origin or the origin will always be 0. So 0 will always be 0. You will not be able, there are cases where you'll be able to shift it, but that's outside of linear algebra. So we're going to be working with like transformations where like it has to be 0. So 0, 0 is equal to 0. 0 is 0. That's final. And the other thing is when you're also like doing some transformation, because they are linear transformations, we are not supposed to be going into some areas where we get curves instead of lines. And so that part you will not be learning. You will not be having some, or to do examples, you don't have to deal with them, because again, the linear transformations is just going to be working with everything having a coordinate origin of 0, 0, and then the change of, I guess, the graph would always be linear. It's a little confusing, but I do know there's a video that will explain it a lot better. So anyways, the next property is the linear transformation of negative v is equal to the linear transformation of v multiplied by negative 1. That is the scalar multiplication property. And then we have the linear transformation of u minus v is equal to the linear transformation of u minus the linear transformation of v. And then lastly, we have we're going to consider the vector v. And if v is a linear combination of different vectors, then that means the linear transformation of v can be the linear transformation of the linear combination of vectors, which is also equal to the linear transformation of one of the vectors multiplied by its constant or corresponding constant, plus the linear transformation of the second vector multiplied by the second corresponding constant, and so on and so forth, all the way to however many vectors they are. And then now lastly, we're gonna be talking about, because these are functions, so what about matrices? Now we're going to be talking about matrices as well, because you could do linear transformations on matrix. So matrix are always somewhere in this topic. Linear algebra always has matrix. So we're going to talk about the linear transformation given by a matrix. So we're going to define our matrix. So we're going to let A be an m by n matrix. The function t is defined by the linear transformation of v is equal to a times v. And that is a linear transformation from the dimension n into the dimension m. So Rn to Rm. Mn, so n from m. And so in order to conform to matrix multiplication with an m by n matrix, the vectors in Rn are represented by an n by 1 matrix or matrices, and the vectors Rn are represented by the m by 1 matrices. Yes. And so this is how you pretty much look at it. So we have our our matrix A, which goes from, it's an m by n, and we have the elements, and it's multiplied by a vector v, which will be represented as a column vector. And then our answer is going to pretty much be like the linear transformation of this a times v. And so the vectors in Rn are basically the column vector, and the vectors in Rm are in the product, or I guess the answer. So one thing to note is, even though we're working with matrices, they still have the two basic linear transformation, which is the zero transformation and the identity matrix. So the zero matrix corresponds to the zero transformation from Rn to Rm, and then the identity matrix corresponds to the identity transformation from Rn to Rn, so n to n. And so yeah, that is pretty much it for linear transformation. This is like, I feel like it was kind of short, but I don't think so. So I'm gonna try to find a bunch of examples that we can do to show some examples showing you how to check if one is a linear transformation. What does it mean by a function not being a linear transformation? How can you tell if it is a linear transformation or not? Finding your image and then finding your pre-image, and what else? And yeah, I think that'll pretty much be all. And then this is honestly, this is like a short chapter, but it has like a lot of things to do, and linear transformations are like broken in a sense that they are really useful. And so this is something that like will probably be like one of the, it's interesting because it's like one of the harder concepts to understand, but it's the most relevant one. So I'll try to find a bunch of examples, and hopefully throughout the week or two, depends. I'll be uploading those examples and working them out for you and help you out. So in the meantime, I will see you guys in the Blackboard.